All right, let's dive into something really fascinating today. We're going to break down how you design a computer network for a modern healthcare company, a really complex, high stakes challenge. And we're going to do it by looking at a real academic assignment, which gives us the perfect roadmap for how to think like a pro, and, just as importantly, how you can prove that you've got the skills to do it. So, this is the big question, right? At the end of the day, this is the problem we need to solve. And it's so much more than just, plugging in a few cables. We're talking about building a secure, reliable data bridge across an entire ocean. This is where network design gets really interesting. It's part science, part art. So to make this real, let's meet our company for this case study, Medinet Health Services. Now, they're a UK-based healthcare company, and they're growing fast. But with that growth comes this massive technical puzzle, and you're the one who's been brought in to solve it. And listen, the stakes here could not be higher. This isn't just about sending emails or sharing a few files. We are talking about highly sensitive patient data, electronic medical records, real-time patient monitoring, and even live video consultations between doctors and patients. In healthcare, a network isn't just a convenience. It is an absolute lifeline. It has to work flawlessly, secure, fast, and reliable all day, every day. Okay, so here's the setup. On one side of the pond, you've got the main headquarters in London with about 45 staff members, mostly admin and IT folks. Then, all the way across the Atlantic, there's a brand new diagnostic clinic in the US with 25 clinical and admin people. So you've got two different countries, two totally different functions, but they absolutely have to work together like they're in the next room. That's our challenge. So, where do you even start with a project this big? Well, you start with a blueprint. Seriously, just like an architect wouldn't build a house without a detailed plan, a network engineer has to lay out the fundamental structure first. These first few choices are huge because they impact everything else down the line. And for this assignment, you have to justify every single one. First up, you've got to pick your topology, which is really just a fancy word for the map of your network. A star topology is kind of like a bicycle wheel. Everything connects to one central point. It's simple and easy to manage inside an office. A mesh topology, on the other hand, is more like a spider web, with tons of interconnections. It's way more resilient if one connection fails. So for Medinet, what's the play? Well, a smart design would probably use a star topology inside each office, but then use a super resilient connection between the UK and the US to make sure that critical link never ever goes down. All right, next up, architecture. This is basically the system that manages all the data. You know how at home you might just share files directly between two laptops? That's called peer-to-peer. For a serious organization like Medinet, no way. You absolutely need a client-server model. Having a central server gives you the control you need for security, for managing who sees what, and, most importantly, for protecting those patient records. For a healthcare company, this is pretty much non-negotiable. Okay, so we've got our map, we've got our system, but now all of these different devices need to speak the same language so they can actually communicate. In the world of networking, this language is called a protocol. Think of it as the official rules of the road for how data gets from point A to point B. And the undisputed king of all these rulebooks is TCP/IP. It's not just one rule, it's a whole collection of them. And the real genius of it is how it works. It takes your data, breaks it down into thousands of tiny little packets, sends them across the internet, and then perfectly reassembles them on the other end. It's this system that makes the internet so incredibly powerful and resilient. It's the foundation of everything we do online. Let me ask you this. Do you have your best friend's phone number memorized? Probably not, right? You just have their name saved in your phone. Well, DNS is the exact same thing for the internet. It's the internet's address book. It translates the website names we can all remember into the long strings of numbers, the IP addresses that computers actually use. Without it, browsing the web would be impossible. And this one is a real lifesaver for anyone managing a network. Think about when you walk into a coffee shop and connect to their Wi-Fi. You don't have to ask the barista for a special IP address to type in, right? It just works. That's DHCP doing its job behind the scenes. And for Medinet, with 70 employees and who knows how many devices, this isn't just a nice to have, it's absolutely essential. Okay, so we've got our grand plan all laid out on paper. We've chosen our topology, our architecture, our protocols, but you wouldn't start pouring concrete for a huge bridge without testing a model of it first, would you? Of course not. And the exact same logic applies here. This next step is a really key part of your report. And this is where the real magic happens, with simulation tools like Cisco Packet Tracer. These things are incredible. They let you build a complete virtual version of your entire network design in a digital sandbox.
You can connect the London office to the US clinic, configure all the routers and servers, and actually test to see if data is flowing correctly, all before you spend a single penny on real hardware. This is how you find problems before they become real expensive problems. So we've gone deep into the technical design, but now we need to switch gears because this is all based on an academic assignment, right? And that means there's another crucial layer here. It's not just about what you design, it's about proving you understand why you made every single one of those choices. And this is where we need to talk about the rules of engagement. So let's be super clear about how this module works. It's split into two big pieces. Assessment 2, worth 60%, is the practical, hands-on portfolio where you actually get to build things. But before you can even get to that, you have to nail Assessment 1, the design report, which is all about the stuff we've just been talking about. And don't sleep on this report. At 40% of your total grade, this is a huge deal. This is where you have to justify every choice you made, back it up with solid reasoning, and prove that you can think like a real network engineer. Getting this right is absolutely critical for your success. Okay, now for what might be the single most important rule in this whole assessment. And I really need you to hear this one. The rule is simple, and it's not a suggestion. No generative AI tools are permitted. The entire point of this is to show what you know, what you can design, and how you think. And here's the official warning. This is about more than just a grade. It's about academic integrity. When you get a job, a company isn't hiring an AI. They're hiring you, your brain, your skills, your ability to solve problems. Using an AI to write your report doesn't just break the rules. It means you're cheating yourself out of the very learning you're here for. And be aware, if a high AI score is detected in your work, you may be called in for a meeting to explain it. You don't want to be in that position. And all of this leaves us with a really big, fascinating question for the future, doesn't it? As these tools get more and more powerful, how are we, as students, as professionals, as a society, going to define what original work even means? Thinking about where that line is and why it's so important to have one is a challenge we're all going to be dealing with for a long time. Thanks for tuning in.